welcome to another Cosmology talk. This week we have James Alvey, who is a postdoc at the University of Amsterdam. He'll be speaking on sort of all things Big Bang nucleosynthesis, partially on the new-ish element abundance measurements of the lunar collaboration and what we as cosmologists can use them for, and partially his own recent work using those measurements to constrain dark sectors that would alter the thermodynamics of the early universe and thus alter those abundances. So welcome, James. Do you want to tell us briefly what you'll be talking to us about today?
My part in all of this BBN story kind of was started back in 2019 when I was doing my PhD at King's, along with some excellent collaborators there, who I'll talk about in a sec. But we looked at constraints on these MEV kind of scale, because that's the right energy scale to pick out when you think about BBN, dark sectors, and how they can impact the abundance measurements. But in the interim, kind of fast forwarding to 2021, firstly, I'm very happy that those constraints got used plenty, which has been really nice. But secondly, the lunar collaboration, so they measure reaction rates for nuclear reactions, things like deuterium going to helium, things like that. They made a new measurement and they significantly reduced some of the errors that were really dominating the theory predictions. And we thought, this is an important thing that we need to understand how this decent step forward in BBN theory really affects our constraints. And from that, of course, it's been a nice learning process to understand the context of all of that. So that's, my aim today a little bit is to discuss, of course, the stuff we did, but also mainly the context of all of this discussion and why BBN in 2021 is different to BBN in 2019, for example.
There were only two things that people did take away from the talk today. What would you want them to be, that if they're remembering it 6 months from now?
Yeah, sure. So I think the first thing is that there are many different elements to BBN, and especially if you are kind of like myself, a kind of beyond the standard model practitioner in this regard, it can be often quite easy to focus on modeling the impact of your new physics on BBN. But it's worth bearing in mind that there are many other elements. There are the measurements of the abundances, for example. There are the nuclear reaction rate uncertainties or measurements, and all of those play an equally, if not kind of more important role in ultimately what you deduce about the scenario you're interested in. So I think, the first message from especially this 2021 work is that it's worth trying to understand these updates in the BBN community. And of course, part of the role of that is from the people putting out the research along those lines. But it's also to really understand how that impacts what you're doing and where it might lead in the future. So that's kind of number one. And the second thing is that, experimentalists are doing great things. So it's actually worth keeping an eye out for, often if you can really reduce your theory prediction, for example, you might be able to say more about your scenario than you thought. But that does rely on you keeping in touch with these issues and measurements.
You've sort of already been talking about why this is important, but let's go into more detail now about why this is important for us here in 2021.
Sure. So I think BBN just as a probe both of standard model physics and BSM physics, but I think the main real crucial consequences of in particular things like the lunar measurements actually come for standard model BBN, and using BBN as a kind of so-called baryometer. If you want to compare, for example, inferences of the baryon density, like a fundamental parameter in cosmology from the CMB to BBN, you need to understand the dynamics of BBN and you need to have excellent control over all of the different processes go on there. And lunar, the role that it plays is that it really pins down one of these key bits of physics, which is the deuterium kind of production and annihilation rates. Now, there's more context to that, and hopefully we'll get into that a little bit later. The context is that when you go through this process, it's not super trivial. Actually, there are a number of different ways to approach this. And there's a few kind of key groups across the world, some in Italy, some in the US, some in France, who went through, with the same data and came to somewhat different conclusions about inferences about the baryon density from, BBN. And, I think this is interesting. It's a crucial parameter, right? It is a fundamental parameter in lambda CDM, and it's also the only free parameter in standard model BBN. So coming to a consistent view on this story, even in the context of the standard model, of course, like my personal interaction was kind of BSM, but coming to a robust conclusion in the context of the standard model, I think is really important for using BBN as a precision probe of standard model and BSM physics.
When you say it's the only free parameter, is the baryon to photon ratio then like a constrained parameter because we've measured the temperature of the CMB so well, or is that not somehow an important parameter? Or
So the baryon to photon ratio, and I'm kind of using that interchangeably with the baryon density. You know, one other way to see it is that you could actually take the baryon density from the CMB. You know, you could use that determination and plug that into BBN. Then there are no free parameters in standard model BBN. But if you do want to treat BBN as an independent kind of probe, you should let that vary and see what happens.
yeah. And then I guess if you're going beyond the standard model, then the number of photons might be different because you might have lost or created them.
Yeah, exactly. Or any other physics, you know, neutrinos or electrons.
Shall we get into the details then?
Right. So, you know, to pick up on this story, I kind of want to ask this question, which is, what can you really measure with BBN in 2021? So this is related to some work that we did with Nash Sabti, Miguel Escudero, Diego Blas, Malcolm Fairbairn, back when I was at King's. But that was back in 2019, and we recently released an addendum on this in 2021, and the idea was to include these nuclear reaction rates. So this next portion is hopefully to tell that story about what the context of that is and why we did it.
I just want to point out, I love the fact that you had an addendum rather than a whole new paper. It's so cynical to write a whole new paper when perhaps you're just updating a small piece. And maybe in the mid 20th century, you had to write a new paper because it had to be sent around the world, blah, 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 blah. But in 2021, there's just no reason that we have to do a new paper for every tiny little piece of knowledge. I mean, it even saves us trouble of having to write the introduction again, but in different words and all of this, when you can just say, hey, old paper, still relevant, new results, here's just a new section.
100%. I mean, that's what we want to do. We almost thought about submitting it as like an appendix or something, but that messed up with all the publishing. Like, you can't do that, it turns out. But yeah, I mean, there was no point in writing a new paper. It's just like, oh, we did this check because we didn't have the data in 2019, and now we do. So we're going to use that. So, you know, this is the real question. Why now? And I think to understand why an addendum in 2021 was the right thing to do, it's good to think about the current status of BBN and all the different parts that go into it. So first off, crucially, if you want to use BBN as a probe, you really need measurements of the abundances. So in particular, kind of the 4 helium abundance and also the deuterium abundance. Now, at the moment, from blue compact galaxies, for example, for helium, or quasar gas cloud systems, this is really like a precision probe today. And it's at the level of kind of 1%. I'm not going to talk too much about that, but there are some excellent talks kind of online or slides to explain how that process is done and how to extract that information from the astrophysics. But you know, that's a crucial part of using BBN as a probe of any sort of physics, whether it's in the standard model or beyond. The next part is kind of what we discussed a bit before, which is that there's a theory element to this. And within the standard model, this is now super well controlled. I'm going to mention some of the different elements that go into kind of BBN theory in 2021 later. But at the level of kind of predictions, there's really only one free parameter, and that is the baryon density, or kind of equivalently, the baryon to photon ratio. Most relevantly to our work, there's also updated measurements of key parts of the reaction network. And this is the Lunar Collaboration's role in this. And I say we'll talk about that more later. That does require some context to really understand, you know, the implications. But for now, you know, the fact that there are updated measurements that came out in 2020 is kind of part of the key. And then, you know, finally, just from a standpoint of using BBN as something to learn about physics, you know, it's very sensitive to a wide range both of particle physics but also cosmological effects. And all of the above reasons, the fact that you have good measurement of the abundances, good theory predictions, and also, you know, now very good control over the rates in the reaction network, that makes the BBN like a very clean probe to compare either to other data if you want to do standard model physics, or to look for unconstrained new physics, which was, you know, our motivation for it.
I kind of have a couple of questions at this point. So when I was growing up in cosmology, the primordial lithium abundance was a problem. Is lithium not as sensitive now? Like, are these other probes so much better measured that lithium's kind of not important?
I think lithium is still a problem. It depends on, you know, I think the measurement of lithium is not at the same robustness as helium and deuterium, mainly because of these issues of, do we know exactly how it's, for example, produced and destroyed in young stars? However, that by itself is not a reason to dismiss a lithium problem at all. So I think that's actually part of kind of outlook as to where to go, where things might go next. But yeah, I think that remains an issue, an open issue in BBN, either measurement, perhaps it will turn out to be, or theory, one of those two.
I guess the other thing that I find kind of interesting is that BBN is so useful as a probe that new nuclear physics measurements actually do make it a better probe, if that makes sense. I mean, if it makes sense as to why I find that surprising. I mean, it's one could imagine an alternative scenario where the uncertainties in the cosmology were just so large that yeah, okay, Luna went out and measured some cross sections better, and it's like, okay, I mean, our negligible source of error is now even more negligible. Like, thanks. Like, if you went and measured the mass of the electron slightly better, it wouldn't necessarily change cosmology that much. But instead, it's the other way around, that these were the leading problems.
I think that's, one thing that's worth saying there is that's testament also to the first point on this slide, which is that one of the reasons that you've got into this position where measurements of, literal nuclear reaction rates become important is because the errors on, in this case, deuterium from these like quasar gas systems are so good. And, those are some people like Ryan Cook, for example, who work very hard to get the observing time to make that measurement. And deuterium, for example, has very good prospects in that regard. There is helium, it's slightly less clear, but actually for deuterium, there are prospects to reduce that, below the 1% level. And then these lunar reaction rate measurements take on even more significance in that regard.
Is there still like an issue at all, or maybe I'm just being naive here, but yes, okay, you can measure the helium in blue compact galaxies and the deuterium and hydrogen and quasars. How it's the same as that lithium problem. How do you know that that's primordial and not primordial?
I mean, I think one thing you have to do is kind of play a bit of Occam's razor game and say, okay, I also have BBN predictions, right? And the BBN predictions agree very, very well with my measurements. I have no reason to go beyond that, given that I think the measurements, I've done everything I can to ensure that measurements really are measuring primordial abundances, and I've done everything I can to control all the theory uncertainties in my BBN predictions, and they come to the same number. I don't know, again, it's not a proof, but...
Yeah, I was wondering whether there might be some sort of like redshift convergence plot that like as you go to earlier and earlier times, you're converging on some number.
I think in terms of, it might not be redshift, I think there is a kind of metallicity convergence plot. So typically in these systems, you go and look for very low metallicity environments because that indicates like less star kind of activity. So I think, that's your measure in that regard. Yeah, so this is kind of the question I'd like to pose today a little bit, which is in this context. So, not in general, but in the context of 2021 with 1% errors in the measurements and very good determination some of the reaction rates. What can BBN really be used to measure? And my argument is that it can kind of be used to measure a combination of a couple of things. You can kind of measure or at least be sensitive to the reaction rates, be that weak or nuclear interaction rates. But you're also sensitive to the expansion rate of the universe. And that gives you, there's a little caveat here, of course, that the effect that you're looking for, perhaps it's in the context of new physics, that has to be large enough compared to your measurement errors. But these are typically the things it's sensitive to. And this is kind of what I'd like to focus on. Right, so the rest of this little bit, we kind of went over the intro, which is like, why now? And what can BBN do, or at least what is it potentially capable of doing? To go beyond that, I do think it's useful to think about the physics of BBN. And in particular, there are many aspects of both cosmology and particle physics that go into a full BBN description. I'm going to take a slightly smaller focus and focus mainly on this reaction network, of course, for the reason of that is where Luna has the biggest impact in that regard. And then finally, take some outlook, given that both on Luna, the implications for some of our work, and then just some conclusions or like recommendations, that sort of style, just to finish off. Okay, so the physics of BBN, it kind of splits into two parts, I think. So you have cosmology, where you have neutrinos, electrons, positrons, photons, and you also have dark matter and dark energy, although we'll talk in a sec why actually, as far as BBN is concerned, those aren't really your kind of the focus. And then you have this nuclear reaction network, which can typically look relatively complicated, that sits almost within this system. You have neutrons and protons that interact, and then you have nuclear reaction rates that go into all of this, and somehow you have to put this picture together and solve it in a consistent way. And I think on the surface it can look like a relatively complicated system, but there's the following kind of key idea. And the key idea when you are looking to solve for BBN abundances is the fact that you can actually solve the cosmology first, and you solve for the thermodynamics. And the cosmology at this time is neutrinos, electrons, positrons, and photons dominantly, because this happens during radiation domination. And then you can solve for the dynamics of the nuclear reaction network, almost using your kind of cosmology as like an input into the reaction network. I think, that's not something that's immediately obvious or necessarily true, but in this case it happens because the nuclear reaction network has abundances that are always proportional to like a baryon density, and in radiation domination that baryon energy density is completely subdominant compared to neutrinos or photons, for example, and indeed like dark matter and dark energy. They are subdominant components.
Like, this feels like I might be asking a dumb question, but ρ_PL, is that a typo? Should that be pH? Or?
I should have said that. So I using that to generically describe the plasma. So I should have said. But yeah, that's kind of electrons, positrons, and photons. I'm being a little bit careful there because electrons during BBN do go from being a relativistic species to a non-relativistic matter one. So it's not quite true that, for example, baryons are always subdominant compared to electrons, but they are compared to the plasma. But yeah, I think there's the other non-obvious point about BBN, which is the fact that whenever you see it, you never see a spatial dependence to it. And again, that's the fact that BBN happened like early enough that all the anisotropies are completely subdominant compared to the kind of homogeneous description. It's something that you never really think about until you think about it, and then you're like, why is that true? The reason is just if I propagate back information from the CMB, I can be really confident about these facts, that radiation domination is the dominant energy density in BBN, and that the perturbations are very small.
If I was thinking about this from first principles, I might have suspected that there were, and in fact, now that I'm thinking about this, I don't know the answer to the question I'm about to ask. Not so much that the like gravitational anisotropies would be relevant, but literally just shot noise in terms of there's not an electron at every single point in space. There's not a proton at every point in space. So you might get some induced anisotropies because, there's a proton here and there's not a proton here. And so the reaction rate here will be slightly different to the reaction rate here just because there's different matter. Yeah, so I never thought to ask that question before, but why are there not induced anisotropies during BBN? Because I know that in other phase transitions, there might even be gravitational waves produced, and people talk about that all the time. So yeah, what is different about BBN?
I think it's a statement that, especially when you're talking about the electromagnetic plasma, things like Compton scattering at this point are so efficient that you can transfer, if you want to call it information, whatever you want to call it, you can transfer information throughout your pretty dense plasma very, very efficiently and very, very quickly. And that's ultimately why a homogeneous description is relevant. And the fact that you have a very thermal system. It does deviate, I'll talk a bit later, it does deviate crucially from equilibrium, but in some regards it doesn't deviate too far. Right, so you have the cosmology, and the nuclear reaction network in principle sits inside it, but it doesn't really sit inside it. And really, the picture kind of looks a little bit more like the following, which is you can solve for the cosmology, in particular the dynamics of neutrinos, electrons, positrons, and photons. And really the result of that you need is the temperature to time relation. I'm going to emphasize that a little bit more in a sec, but it's a statement that actually many events in the nuclear reaction network occur at kind of similar temperatures. Actually not much BSM physics, for example, even would change when the deuterium bottleneck was overcome. But the time at which they happen is very, very sensitive to the cosmology, the expansion rate of the universe, and the dynamics of the plasma. And actually, because this nuclear reaction network is out of equilibrium, for example, that means that your abundances, your final abundances, are very sensitive to this mapping between temperature and time. And we'll talk about how to get that from cosmology. If you want to go into a little bit more detail, and that's why it's in brackets, you also probably want not only the plasma temperature, but you do also want the neutrino temperature too, which is typically not the same as the temperature of the photons. And the reason for that is quite simple. It's because the neutrino temperature and the photon temperature, or more specifically their ratio, typically goes into calculating the weak interaction rates, things that between neutrons and protons, for example. So you do need the neutrino temperature as well, which takes a bit of work. But in spirit, what you need is a temperature to time relation that you can then use as initial conditions for the reaction network. So this is not really the focus, but it is a kind of important enough part that it's worth reviewing very briefly. So how do you actually go about solving the cosmology? There's kind of two steps, I think. And the first one is to solve for the thermodynamics of the system. So I put in neutrinos, electrons, positrons, photons, and I know the interactions between them. For example, Compton scattering between photons and electrons, or neutrino electron scattering between the neutrino and electron plasmas. And I can use the fact that entropy is conserved in this kind of adiabatic expansion of the universe at this point. On the right-hand side, I've flashed an equation. I'm not really going to focus on it here, but it's just to show that you can do a couple of interesting things. And the goal is to get A as a function of t, so the scale factor is a function of t. But this is to kind of highlight what BBN in 2021 looks like. And it looks like the following, which is that you can take into account some very non-trivial effects in this plasma. One of the very difficult things to do is to take into account the fact that neutrinos, they do decouple, which we'll talk about in a sec, but they don't decouple instantaneously. There is some shared kind of entropy between the electromagnetic plasma and the neutrinos, and you have to take that into account somehow. And you also have things like plasma effects. So the fact that an electron is sat in a plasma of photons means that it gets some correction to its mass as a function of the temperature, for example. All of these things are possible to include in the thermodynamics, and this is part of this statement that theory predictions today are very, very precise, and they include a wide range of physics. But they do sit at the level of kind of thermodynamics, and I say ultimately, once they're taken into account, the result is quite simple, and it's the scale factor as a function of temperature. The next step is to kind of then take that, and in the meantime, you can also write down the energy densities as a function of temperature, for example. Here, PL is the plasma, which is gamma plus electrons. And you can solve the Friedmann equation. And really, the only role here is to obtain the following. So you take A as a function of temperature. You know the energy densities as a function of temperature. And solving the Friedmann equation, you really are just looking for either the scale factor as a function of time, or equivalently, because you know the scale factor as a function of temperature, the temperature as a function of time. And this is your input into the nuclear reaction network. But yeah, so, what's the result of this? I say I've kind of put a little bit in standard model BBN. You can move some of these numbers around if you do some beyond the standard model physics, but just for now, we'll view this as kind of like a result. And the result is this relation, this mapping from above the white line to below the white line. So, you have these key events, and we'll go through them shortly. We will go through them. They're important both for kind of the cosmological evolution, things like neutrino decoupling or electron-positron annihilation, and then crucially for the nuclear reaction network kind of evolution of the abundances. But you get this mapping between the temperature at which these things happen, which I say is relatively unchanged depending on what sort of physics you put in, and the time at which they happen. And it's this relation between the temperature and the time that's actually the cosmology dependence in your problem. And I say we're going to argue later that because BBN is an out of equilibrium process, it really does know not only about the temperature, but it also knows about the time between things. So, an exercise is worth thinking about. If I look at an equilibrium system, I can tell the difference between an equilibrium system at one temperature compared to another. I might look at like the abundance, for example, of something, if it drops below its mass, something like that. But I can never tell in an equilibrium system how long that process has taken. The same is not true for an out of equilibrium system, and this is why the temperature to time mapping is so important in BBN. Okay, so, the first important event that comes about in the cosmological evolution is this neutrino decoupling. And we kind of alluded to it before, that at some point in the evolution, in particular as the temperature drops, neutrinos are no longer kind of in contact and they can no longer communicate with the electrons and the photons. It's worth thinking about how neutrinos actually, actually share energy with, for example, the electrons and positrons, and it's through these sort of scattering processes. Now, the rate of these processes scales, it's a weak interaction and it's temperature dependent, like many interaction rates, but it scales typically like G Fermi squared times T to the fifth. Now, to understand when this becomes inefficient, we have to think about the Hubble rate as well. So all of these interactions are happening in a box that's getting bigger, and as soon as the rate of these interactions is kind of small in comparison to the expansion rate, they typically freeze out, as they'd say, so we'll use that concept in a bit as well, but they freeze out, and after this point, neutrinos and electrons can no longer efficiently share your energy. That leads on really nicely to kind of the next key cosmological event, which is electron-positron annihilation. And this is where, below the electron mass, effectively the equilibrium for the reaction that's shown, so electron-positron pair goes to two photons, shifts really, really far to the right. And the reason for this is very simple. It's just because photons that are thermalized typically just don't have enough energy to pair produce the electron-positron pair. But the result of this, as far as cosmology and BBN is concerned, is the following fact: that neutrinos at this time, we argued that they were decoupled at higher temperatures. They no longer see this kind of entropy or energy density that comes from the electrons and positrons. And that means that the photon temperature is boosted, but the neutrino temperature crucially isn't. And so after this point, you have neutrinos that have a temperature that is less than the photons. So that's the cosmology out the way. It's now time to kind of go to the relatively complicated, I think, looking reaction network. So at the end of the day, we're interested in using BBN as a probe, and we need to understand how you produce things like helium-4 or deuterium, or maybe in the future, if we have good measurements for them, things like helium-3. But getting through this reaction network takes a little bit of understanding. Fortunately, there are some simplifications, much like the cosmology reaction network split, that you can make to kind of make this process a little bit easier. So the first thing you can do is that you can split the network in two, and it's this kind of vertical line. And above temperatures of about 0.1 MeV, you can solve just for the dynamics of neutrons and protons, and we'll talk about that in a sec. And then below about 0.1 MeV, once you've overcome this so-called deuterium bottleneck, which again we'll review in a couple of slides, you can then solve for the kind of full dynamics of the actual nuclear reaction network. And I've highlighted here, for example, where the lunar rate comes in. So this is just to motivate, why do we want to focus on this little square of reactions that come about? And it's this is where lunar plays a role.
I guess can I ask one maybe stupid question on that previous slide? Yes, it's complicated for me to look at as a human being, but it doesn't seem inherently complicated for a computer to just have each interaction rate coded up. So why is it helpful to have this pre-0.1 MeV and post-0.1 MeV split, and not just have the powerful computer calculate everything at all times?
So I think you definitely can do that. That's definitely an approach. With kind of modern, I think, precision approaches, it's not really beneficial to track the abundances of every single element at all times. But there's no kind of reason for that apart from computational efficiency. It's just the fact, for example, if you want to track the abundance of lithium-7, really you don't need to track it until very late on in the process. And you can track it, but you're going to find that the abundance is practically zero. Complicated, I mean, in the sense of, there's a lot of, I think, potentially, especially from a theorist perspective, there's a lot of kind of potentially unfamiliar nuclear physics going on here. That's what I mean in terms of complicated. And having an intuitive picture of the dynamics, in particular, of the square part of the network on the right-hand side of the line, I think that's challenging even for kind of like people who are familiar with the different reactions. So like predicting how much, intuitively, how much tritium, for example, I end up with. I think that's quite a complicated task. So I say you can solve it above 0.1 MeV and below 0.1 MeV. So we start off with this kind of simplified neutron-proton system. So again, there are a couple of regimes here. The first one is at temperatures typically above kind of 0.8 MeV, say before kind of 1 second, at that time, neutrons and protons are in their thermal equilibrium abundances. And the reason is because the three reactions there are very efficient at interconverting protons and neutrons. Said in the way of neutrino decoupling, the rate for these reactions is much higher than the Hubble rate at this time. But this is not always true, and actually, until around 0.8 MeV, this is true, but then these reactions fall out of equilibrium. And the following plot highlights that a little bit. So we're looking at the neutron to proton ratio, and the yellow dotted line is the kind of equilibrium abundance that you would expect if these reactions were very, very efficient. And if you want to think about that for a little bit, this is probably a good thing, because otherwise we'd end up with no neutrons to kind of make helium out of. So we kind of needed it to go out of equilibrium. But this is the actual abundance that you see, and I say it's simply for the reason that those reactions that inconvert proton and neutrons become pretty inefficient at some point. And it's around this kind of temperature here, this time of kind of 0.1 to 1 seconds, that this tends to happen. But this is not the end of the story for neutrons and protons. And if you drop the temperature a little bit further, or wait for about 10 seconds into kind of the early universe evolution, then it actually turns out that not only do the reactions kind of fall out of equilibrium, but actually the kind of backwards reaction of protons being converted into neutrons is not very efficient. And actually, below these temperatures, the only process that can really happen is neutron decay. So that means that until you get to this point, which we're going to talk about in a second, really the only thing happening in the whole BBN nuclear reaction network is that you have these neutrons and protons, which set the abundances kind of that we saw on the previous slide, and neutrons just decay, because that's the only reaction that's actually kind of relevant at these times. And you can kind of see that here. This is just tracking the neutron abundance, and this yellow dotted line, the blue is just the neutron abundance, or in particular compared to baryons, but just in the neutron abundance. And this is the abundance of neutrons if you just let it decay with some decay lifetime tau n. So, you see after this kind of 10 to 50 seconds, for a good chunk of time, about 150 seconds, the only real dominant process that's going on is neutrons are just decaying into protons. So, if you let this run on and nothing else happened, we're going to talk about what else happens in 2 seconds. If nothing else happens, the neutrons would eventually just decay away, and the only baryonic component you'd be left with would be protons. And I say, in this region, the neutron decay really is the dominant process that's going on. But fortunately, something does happen. Otherwise, there would be no way to end up with the heavier elements. And the idea is that we have to get over this so-called deuterium bottleneck. Deuterium has a binding energy of a couple of MeV. And that means that, below that temperature, it's kind of energetically preferential to make deuterium out of a proton and a neutron. It's better to be on the right-hand side of that equation, kind of from an energetic viewpoint. But if you actually look at the evolution, which I'll show in a second, you really have to wait until temperatures kind of, almost kind of a factor of, factor of kind of 50 smaller to actually significantly produce any deuterium. So the question is why? Why does this happen? And the answer is photons. And the answer is the fact that there are way more photons than there are baryons. So at a typical energy of, say, 0.1 MeV, the average photon does not have enough energy to kind of dissociate the deuterium. However, there are about 10 to the 9 more photons than there are baryons at this point. So it means that even though the kind of average one doesn't, actually the tail of photons, which is where the capability of kind of dissociating this is, the ones that are in the very, very far end of the kind of whatever kind of distribution you're considering, there's still plenty of them around. And this is ultimately the reason, there is, even though the average photon doesn't have enough energy, there is still plenty of them as kind of parameterized by this baryon to photon ratio. And this is the fact that deuterium synthesis is kind of delayed compared to a couple of MeV is excellent evidence for a very, very numerous, thermal bath of photons around this time. If that was not there, if the baryon to photon ratio was 1, for example, there was 1 photon for 1 baryon, deuterium could be produced at 2 MeV without any issues. If you wanted a quick way to estimate where this point MeV is, the thing that you might do, for example, would be to integrate the number density of photons with an energy above 2.2 MeV at a given temperature and compare that to the number of baryons. And you're going to find that, you typically get this factor of something about 50. And that's the point at which deuterium can then be, synthesized. The problem is not synthesizing it. This is the point. Protons and neutrons are more than happy to make deuterium at this point, just from an energetic viewpoint. The problem is once you make it, you don't keep it. So to kind of see how that actually goes ahead, here are the evolution of the abundances. So the yellow curve is just the neutrons. So we kind of saw the evolution of that, and the top curve is the protons. So in this intermediate regime where neutrons are decaying, you see that protons they just decay into protons. So the proton number density just increases in exactly the same amount that neutrons decrease. But then eventually you get to this point at about 200 seconds or about 0.078 MeV, where suddenly you can produce deuterium. And I've kind of scaled it up a little bit just to kind of make the point. But you see that very, very quickly the production of deuterium ramps up, and then it's used up again. And we'll think about what happens to it in kind of the next slide. And I say it's only after this point, about 200 seconds, that you really start to have a dominant production of deuterium that actually hangs around for any reasonable amount of time. And that's exactly what you need. Some people call deuterium a kind of catalyst. So you create it and then you use it up to go further, so it's not like it stays around, but you do need enough of it in order to move further on in the network. So we're finally at the point where we start to see, again, lunar, but also we have enough deuterium to really start thinking about the dynamics of this kind of square part of the network, and crucially where you end up with something like helium-4. So this kind of proceeds as soon as you have plenty of deuterium, and because the binding energy of helium is so high, so it's about 28 MeV, that means that these temperatures of, 0.05, 0.06 MeV, once you make helium, the backwards reaction rate is actually very small. It goes like something like e to the minus binding energy divided by temperature. So, the forward reaction to go to this 4 helium state is very much preferred. And in terms of abundances, you see the following. So I've just, there's the deuterium just to give you a reference point for some time. Here's the neutrons plus protons, so the sum of those two abundances. Here's the 4 helium, and this shows you basically that all of the neutrons and protons, you use up all of the neutrons that you can, and they all go into kind of 4 helium, that effectively. So this is the physics of kind of producing 4 helium. I think now it's worth taking a thought, and I've kind of just said, you use up all of the neutrons and it's super efficient to make 4 helium, and then you ask me the question of, but isn't lunar measuring deuterium rates? So why are they so important? I think, this is kind of the next step, and this is the step of doing precision BBN. 4 helium is, very much the dominant abundance for basically any realistic model of BBN. But deuterium, 3 helium, tritium are still produced in trace amounts, and we can actually measure those trace amounts. This is this quasar gas cloud system. That's the importance of that, is the fact that even though the abundance of deuterium might be 5 orders of magnitude below that of helium, it's still a very relevant abundance for understanding the dynamics of the BBN network.
The one question that maybe I would have asked, why is it that direction that was the one that was needed to be better measured and not the D to 3H direction? But maybe it's just that that is an important thing to measure, and it just needs to be measured better. I don't know.
Yeah, no, so, I mean, it's a good question, and I kind of touch on it a little bit later. The answer is that the 3 reactions that you see, that if we just think about deuterium for a sec, you do have to worry about the others, but if you're just worrying about deuterium, and the reason you might worry in particular about those is because deuterium is the element that you also have the very good abundance measurement for. You don't actually have great abundance measurements for helium-3, for example. So actually, the two on the furthest right, you might not be so kind of concerned about measuring super well, but you are really concerned about measuring those 3. And it turns out that the status kind of pre-2020, pre-lunar, was you had those 3 reactions. So D plus P goes to gamma plus 3 helium. I'm going to enumerate them because I think it's kind of useful. Deuterium plus deuterium goes to neutron plus 3 helium. So they're the 2 on the upper arrow. And then deuterium plus deuterium goes to proton plus tritium. Now, you have those three reactions, and you have some uncertainty, some like measurement reaction rate uncertainty associated to them, which gets propagated to your prediction in the deuterium abundance. And it turned out that kind of pre-2020, the one that Luna measured there was the absolute dominant theory uncertainty. So the answer is that the others were just measured better than the one that Luna measured. So, you know, the reason why Luna is so important is because it reduced basically the theory error in that part of the reaction network by a factor of about kind of, I think it was a factor of about 10.
Were Luna directly trying to improve Big Bang nucleosynthesis, or is there some other reason why nuclear physicists care about this particular reaction rate?
I'll show the Luna plot in a second, but the energy range that they, you know, really focused a lot of effort into measuring was exactly the BBN energy range. You know, I think it's a quantity that, of course, is useful to know regardless, because it's a standard nuclear reaction that can occur. If you want to think about energy range for a sec, you need to basically, there's an energy range between 0.066 MeV and 0.078 MeV. That kind of corresponds to some energies for these reactions. In the lab, that really does correspond to an energy range that you have to choose to target. So yeah, I think it was very much kind of on purpose.
Maybe another dumb question while we're on a tangent. It's not possible, or at least if it is possible, you can't do it as well to just like predict this from first principles, from like a nuclear physics theory.
This is not a dumb question. This is part of the disagreement, which is what is the right way to go about using this data? In particular, what's the right way to use this data in conjunction with the other two rates? Because there are two ways to go about it. One way is to use exactly what you suggested. You do some theory predictions based on, whatever kind of perturbation theory models you want to use, for example. Or you can take a kind of data-driven approach, purely data-driven, and you only use data that's available, and you basically take no theory prior view on what the rate should be. You basically just make kind of data-driven fits. And it turns out that those actually give slightly different answers. So it's certainly not a daft question at all, and I think actually it's right at the crux of the current debate, which has kind of evolved since the Luna measurements. A word that you might see in this regard is like Marcucci rates. That's kind of the theory prediction for D plus gamma goes to 3 helium, just to put some terminology on it. But yeah, I think, that's a crucial part of it, and I think I'll give a bit of outlook later on, but, that's one of the key points. It's not really, my field is not making these measurements or doing the standard model predictions, but, a consensus that kind of has emerged is that that's one of the things that needs to be pinned down, either with very, very good theory predictions or just improved measurements so that the theory predictions are almost become a little bit like just unnecessary.
Right. I mean, is the argument that they have then that the theorists say that Luna have got a systematic error and Luna tell the theorists that they're making approximations that are invalid, or are they claiming that there's some missing new physics that...
Yeah, no one really disagrees with Luna. So Luna, I'll show the data in a sec, but Luna make a very, very tight measurement of the reaction rate. It's just it doesn't really overlap with the theory prediction for that particular measurement, which means that if that theory prediction doesn't work, and it's a very similar type of system, if you're using the theory predictions, for example, for D plus D goes to proton plus tritium, as opposed to using the data that exists, only the data that exists, are those two approaches compatible? Are they consistent? I think those are the questions that Luna has kind of brought up. The optimal, I think all the nuclear physicists will tell you, the optimal way to go about this is to not have to rely on theory predictions and just measure the rates. But that can be very difficult. So, yeah, sometimes you have to, especially if you want to, so you may have some measurements in a certain energy range and you want to kind of extrapolate to another energy range. There are multiple options for how to do that. But yeah, okay, so we produce helium-4, but as, and one thing maybe just to note here is that actually the total baryon number is conserved in these interactions. Just a nice thing. If you add up N plus P plus 4 helium, that covers basically all your baryons plus trace amounts of the other elements. All that happens is they just get transformed into different isotopes. Okay, but as we said, kind of what you really want to know is what are these trace amounts? In particular, deuterium, because that's the thing that you have an excellent abundance measurement of. And that requires some careful tracking. And one question that arises when you try and do that is, okay, how do I track each of the abundances? And what you need to do in a technical sense is you need to take a Boltzmann equation for each of these isotopes. So for deuterium, for helium, for if you're interested in like lithium-7, and any particular isotope, you have to do all of them. You have to solve these as like a kind of coupled system because of course these reactions can transform one into the other, and you write it down. And then there's a couple of components here. So one of the things, there's a cosmology kind of dependence here, which is just your expansion history. If you just had no interactions on the right-hand side and you took a box of baryons or deuterium and you just let the box expand, the number density decreases. But you have a second component, and this is the kind of crucial part as far as LUNA is concerned, which is that you have reaction rates. That this is an out of equilibrium process, and this is kind of the statement I was making earlier, which is that ultimately the reason that BBN is a good probe is that it's not just a box that has no interactions and it's expanding, and it's not in thermal equilibrium. You are sensitive to these reaction rates. They're not in kind of thermal equilibrium, so you need to measure them or you need to predict them, and then you need to plug them into your system and solve it with some kind of high fidelity to resolve these kind of final abundances. So that's kind of how you want to actually describe the network. And I say LUNA comes into really measuring this quantity on the right-hand side. So, the actual reaction rates. Cool. So finally, we can kind of get to deuterium and look at some data, because there's a lot of context that goes into measuring effectively what is kind of one number, or at least kind of one function of energy. So LUNA experiment in 2020, they remeasured the reaction rate for this D plus P goes to gamma plus 3 helium reaction. One of the crucial arrows in that reaction network. As, kind of maybe discussed earlier, that's not the only one, but it was the one that dominated the theory uncertainty budget for if you wanted to do precision determinations of deuterium and helium-3. So this is this point about the other ones were either better measured or just had less of an impact because perhaps, for example, the rate is just smaller. It's not just about the measurement uncertainty, it's just about how much does the rate control the abundance. And I say previously this D plus dp gamma to 3 helium completely dominated the error budget. So these LUNA measurements, which are the red dots on the plot, in this kind of BBN energy range of 30 to about 300 keV, significantly reduced any uncertainty coming from this reaction. You can kind of see compared to, for example, the green crosses, which are from 2019, in the same energy range, these error bars are significantly smaller, significantly more numerous, and very precise. So these LUNA measurements are very important for controlling these abundance predictions.
Looking at this plot, the thing that jumps out to me by eye is that at the lower energies, these yellow data points and these red data points are completely inconsistent with each other. But then I look at the date of the yellow ones, it's like 1963. Are we just meant to assume that there's some systematic error there?
I think so.
Yeah, okay.
But I think there is something to, if you're talking about inconsistencies, I think there is something to note here, and it's the black dotted line, if you can see it, and if you want to compare that to the red dots, in particular in the BBN, at the top end of the BBN energy range. That's this Marcucci line. This is the theory prediction. Those two are not necessarily consistent. I don't think, no one really has a problem with that. The theory predictions are very challenging. And as I say, the best thing you can do is go and measure it really, really well. But it is, telling somewhat in this reaction that those two things don't overlap. And I think that's something to keep an eye on for the future. Right, so, this is the LUNA data. And, one question that you might ask is, what are the implications of LUNA, especially in the context of standard model BBN? So one thing that happened earlier this year was me and Miguel and Nash, we ran a workshop on this. So it was great. We got to sit back and we hadn't done any of the work, but we got to listen. I think, this was a huge reason for us being able to write the addendum, because we managed to get basically all of the protagonists from LUNA and the three groups analyzing the data. There was also an additional component on the physics of neutrino decoupling, which was super interesting, but not necessarily related to this kind of rates discussion. But, we managed to bring everyone together, and it was hearing these kind of different approaches. And, the answer to the question of what are the implications it does depend slightly on who you ask. And for example, whether that person will tell you whether there's a corresponding tension in the baryon density, because these rates, deuterium is an excellent, what I would call baryometer. It is the thing that really tells you, it's very sensitive to the baryon density. So deuterium and predictions and measurements of it are really the key tool in using BBN to measure the baryon abundance. So, of course, these rates have an impact on that discussion. And I say you can flick through kind of some of the papers that appeared. So this is the Lunar paper. They did an analysis. There's an analysis from a group in the US. There's an analysis from a group in Naples. And there's an analysis from the group in France. And you see that they kind of have different conclusions. So, for example, the French group say, hey, there's a new tension in the cosmological model, perhaps. There's this 2 sigma difference between the baryon density. And I think something that came out of this workshop that was, super interesting was the fact that this was not due to the codes. So they used different codes, but it was not due to the codes. But it was probably due to the way that they dealt with not the lunar rate. So the lunar rate, is very kind of well determined. It's actually really how you deal with the other deuterium rates, and they, whether you deal with them in, the same way, either you take the theory predictions or a data-driven approach, that can change your conclusions. And kind of the outlook from that, and I really recommend going to have it. So I've put like a little link there that you can scan. Go and have a look at some of the slides, because it's easy to learn a lot very quickly, and you pick up the kind of subtleties of this discussion. And I say there's a couple of papers that came out after this workshop, kind of with some recommendations, and one of the key recommendations is exactly this: that these other 2 reactions, which were not, the lunar reaction that started all this debate is not listed there. But those 2 reactions we could really do with either pinning down like the theory uncertainties in them, or just having an excellent measurement at the level of kind of lunar.
Right, yeah. So 2 years ago, these ones were the well-measured ones, and now lunar has obviously improved a particular one, and so these ones are now the leading uncertainties.
Exactly. So now it becomes relevant to kind of take a look at this. How realistic and what sort of timeline that happens on is not so clear. But, I think this is a sort of context that I find super interesting, because now, that's something to look for. You go on the archive and you see, new measurement of D plus D goes to P plus tritium. I think, in 2019, would I have opened that paper? Perhaps not, but now I'm definitely opening that paper. And that's the sort of context that I think has appeared in the last couple of years about, why these rates are important and how to use them.
And do we know of groups who are, now out there, I mean, maybe even the lunar people, I don't know, who are out there intending to measure this exact thing? Because obviously you've made a good case that it's important.
I think lunar are looking at whether they can. I think they will do if they have the capability. I think it's not 100% clear yet who will be the people to do that. This is kind of what raises the question, I guess, why did we write the addendum? We've come out, it's been a long way to why did we write the addendum? But it comes to the question of how do you proceed and keep using BBN as a precision probe, especially if you want to use it at this level. If you want to use lunar data, for example, in making your predictions because they tighten your theory uncertainties, how do you deal with this? And I'm going to suggest in a bit, the kind of the approach that we took was, in some sense, you should consider all of these possible approaches, because I certainly, you will not catch me saying that one is right or wrong. I don't think that's really the correct way to see this. I think the way to see it is kind of along the lines of that they're different, and they give slightly different answers. And actually, from a kind of practitioner point of view of using BBN as a tool to understand my, perhaps beyond the standard model physics, I should almost marginalize over that. That is an ongoing discussion, and I want my results to be insensitive to or at least I want to present the reader or, whoever's using my numbers, I want to present them with the option of whatever numbers come out of that debate. So that was really the motivation for writing, this whole long story about how do you get down to these 3 reactions. That was really the motivation for writing the paper in the end. And it was a useful excuse to learn all about this physics. But yeah, so maybe just kind of a final thing of okay, what are the implications for constraints on our light dark sectors? Yeah. Fortunately, with the discussion we've had so far, it's not so difficult to explain what happens. And so if you have a light dark sector and you have maybe it's coupled to neutrinos or electrons and photons, maybe it decays into them, or it might be coupled to both, then it can kind of modify the history that we've talked about so far in a couple of ways. So the first thing it can do is it can modify like the expansion rate. If you have a particle at the MeV scale, that is a dominant component of the energy density at the the temperatures relevant to BBN. So that can affect exactly this kind of temperature to time relation. And you can see this, for example, in the parameter like n effect. It's something that counts kind of the relativistic degrees of freedom at this time. So it can either boost it in the neutrinophilic case or decrease it in the electrophilic case. And that will change your temperature to time relation. And indeed, that kind of is the dominant force for things like the helium predictions. It can also do something else, though, which is a little bit more non-trivial. So it can modify, for example, the temperature of neutrinos relative to the photons. And again, we kind of mentioned this briefly, is that the weak rates, which cause all of these different timescales and the interactions between them, the weak rates can actually change if you change the temperature of neutrinos. So you do really need to kind of solve for the full weak rate history to understand this effect. And I think that's a little bit more complicated to have some deep intuition for, but you should include it. And the final thing that you can do is you can modify like the baryon to photon ratio. If you decay, for example, into photons in exactly the same way that electron-positron annihilation heats photons up, if you have some light dark sector that decays into them at like a later time, that can change the temperature. And in particular, you can modify the baryon to photon ratio. And that can lead to effects like the following, which is where actually you can decrease, for example, the deuterium abundance. So now you have to think about constraints and where do the constraints come from? And to answer this question about Luna. And it's in the regions where they are dominated by YP or the helium, your constraints. And this is typically at the kind of slightly lower mass end, or you can see where the kind of yellow highlighted bubbles are. That really has very little to do with Luna. And we, when we did the reanalysis, we did find that. There is kind of a couple of cases, though, in particular for these kind of electrophilic particles, where the deuterium predictions can shift up and down a little bit. And, we found that for a bound of kind of 4 to 7 MeV, that can shift by a couple of MeV. Now, this is my point. It's, if you're driven by helium-4 predictions, Luna really doesn't have too much consequence for you because the helium-4 prediction doesn't really change. If you do have a BSM scenario where deuterium is kind of your dominant constraining factor, then actually, taking into account these different approaches for the 3 reactions relevant to deuterium predictions could be quite important. And I say the approach that we took was to basically consider all possible sets of rates and see how the constraints varied. And I think the reason for that is ultimately it's an ongoing discussion, as I said kind of just before. And it's not our place to take a position on that discussion yet. So what we can do is we can, still marginalize over that kind of effective kind of discussion uncertainty, if you want to call it. But yeah, that's kind of all I have to say in that regard. So just kind of flash up some kind of summary and conclusions. The first one is that there are a number of key events, and the physics of BBN is relatively complicated, but they can kind of be delineated, and the cosmology can be solved separately to the nuclear reaction network, as we discussed, and you end up with this kind of nice clear picture of what physics impacts what temperature and at what time. And given this context, so given this kind of good understanding of the physics, then we have precise measurements both of like many of these nuclear reaction rates, but also most importantly, I think, like the primordial abundances. And combined with a good theory prediction, those let us test standard model and BSM physics really very well. In a number of regimes, these are like perhaps the most relevant constraints. And then finally, these new results from Luna, they do require some care. And I think the discussion, hopefully I've made it a little bit clear, is quite subtle. That means that, if I was going to provide a recommendation on it, especially from the point of view of someone who's interested in kind of probing new physics, really, if the aim is to kind of the safest thing that you can do is to really consider all of these things, the theory-driven approach, the data-driven approach, and then look at how your results vary.
Cool, thanks. I was just wondering, another thing that's kind of complete tangent, but in all of your, on the previous slide, all of your beyond standard model stuff increased the helium abundance. Is there any way one might have a model that decreases the helium abundance?
in the context of the physics that we were, so I mean, actually, if you look, there is an intermediate region. It's quite hard to see on this plot. On the right-hand side, about 2 to 3 MeV, there is a tiny dip. Yeah, it's quite hard to do because you have to effectively decrease the energy density of the universe at the times relevant to the BBN. Typically, if you add new light species, they increase the expansion rate, and that's usually the dominant effect. The outlook from a kind of community perspective is towards resolving, and I think also understanding this issue. I think one of the most interesting things that came out of that workshop that we had was, that often these details can be stuck in papers that, if you're not a practitioner, can be quite difficult to follow the discussion. But actually, the discussion is very relevant, and it comes very deeply into like how you make predictions and how you use BBN as a probe. I think a nice thing to do, especially as a BSM community, is to kind of get involved with these discussions, try and understand them, and then you can write better papers because of that, or at least ones that hold a little bit more to the test of time.
Yeah. It might also help the people who are having those discussions to know what is relevant to a community that is using their output.
Indeed, using BBN as a standard model physics probe is, I think it's still relevant today, but it's becoming less relevant given the kind of relative concordance between a number of probes. So, using BBN as a real, given it agrees so well as a standard model, typically as a constraint on new physics in the early universe, I think it's an extremely relevant probe, and therefore like understanding all of the physics. I think typically it acts not so much as a place to look for new physics, but it acts as a way to kind of rationalize your models at those times. There are things that you can't do specifically because the physics of BBN is so well controlled. In particular, I think with reference to things like neutrinos, you need certain properties and temperatures of neutrinos, and you need them to decouple at the right time. All of those things have to be true, and that information comes from BBN. I think it's still a very relevant process today, particularly in the context of kind of the use as a precision probe.
So, okay, final question of what work being done in cosmology at the moment do you think is particularly underappreciated by the community as a whole?
Cool. So I had a good think about this question because I saw you'd asked it in like a number of videos. I think it's a really tricky question. And I'm actually the work I'm going to pick is based on actually the discussion we just had. So about neutrinos and what we know about neutrinos from cosmology. And in particular, this prediction of kind of a cosmic neutrino background. So I think detection of the cosmic neutrino background is something I'm personally extremely interested in. But actually, when you look at the literature, is relatively kind of there's a couple of suggestions of how one might directly detect it, things like Ptolemy or Project 8. It's clearly an incredibly challenging detection. I don't think there's any doubt about that. But equally, the payoff for such a detection is potentially huge. I think any detection of the cosmic neutrino background, we would learn a great deal about physics in, the 2 MeV temperature window in the very, very, very early universe.
You mean even if we literally just measured, not the anisotropies obviously, but just the...
Say you measured the temperature of the neutrinos. I think, you would learn something very deep about physics in the first 1/10 of a second in the universe. And, that strikes me as someone with huge potential, but is actually relatively underexplored, especially on the kind of experimental side.
Yeah. I think this is like a very good answer to this question. Certainly, this is the sort of thing that if it comes up, if like a first year PhD student asks the question at a conference of, could we measure the cosmic neutrino background? Everyone's like, what a silly question. Of course not. Whereas, as you said, if we were clever enough to actually measure it, it would be amazing. So if there are prospects for it, then it's definitely underappreciated.
Yeah, I wonder if, you look at the history of the CMB, and I think the initial reaction to measuring the cosmic microwave background was there's no way that you can measure, especially for the, maybe measuring the cosmic microwave background, like the temperature of the, the monopole, that's fine. But measuring the anisotropies, at the amplitude that they were expected was written off as completely unrealistic.
Yeah. And now we've measured an order of magnitude less in the polarization.
Indeed, exactly. So, these challenges are not new, but I think you look at the impact that something like the Planck data set has had on cosmology, and you imagine even a rudimentary version of that for the cosmic neutrino background. You're looking at probing 1/10 of the second after the Big Bang. That's something that no other probe, apart from perhaps BBN, which is why I kind of was thinking about it, can do.
Thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified. And click like to help with those YouTube algorithms, and share the channel with your colleagues. If you have any suggestions or questions, leave a comment. I'll make sure that James sees them. And other than that, thanks James for the great talk.
Thank you very much. It was great.